Hi, my name is Ramon Nepomuceno, and I'm gonna present my work, which is entitled Enabling Multi-FPGA Clusters as an OpenMP acceleration device. This work is a joint effort between my advisor, Professor Guido Araujo, Renan Sterle, also from UniCamp, and myself. Our work is motivated by the ever-growing interest in high-performance computing. For example, we have the application of seismic imaging. This application consists of mapping and analyzing the characteristics of the surface of the ocean floor using boats equipped with sonars and sensors. As a result, the application generates an image that will be used later in other tasks, such as oil extraction. Heterogeneous systems are widely used in such applications that require high performance. We easily find systems that use everything from DSPs, coprocessors such as Intel, the current TPUs, and even the GPUs that are easily found. However, in recent years, there has been a growing interest in use FPGAs in high-performance heterogeneous systems. Among other reasons, this is because FPGAs have been proven to be a powerful device that can accelerate pipeline applications. But even a powerful FPGA cannot handle very large problems like seismic imaging. That's why we need multiple FPGA architectures, creating a cluster of FPGAs that can be seen as a super FPGA. Moreover, FPGAs to chains are hardware-oriented and unfriendly to software designs. We need a simpler and transparent approach to embed FPGA accelerators into software applications. That's why we propose to use OpenMP task-based programming model for multi-FPGA architectures. We extend it to 1. Enable automatic bitstream data offload to FPGAs. 2. Transparently map data dependence to IP board interconnected. And 3. Allow a seamless flow of data to and from the FPGAs. Before we dive into the details of our work, let's talk a little about the basic concepts of OpenMP and FPGAs that will be necessary to understand the proposal. The OpenMP specification defines a program model based on code annotation that uses minimum modifications of the program to expose potential parallelism. The specification allows the programmer to create interdependent tasks in a no-block way, as seen in this code example. First, a pool of work threads is created with the Pragma OMP parallel directive. Then, the control thread is selected with the directive Pragma OMP single. From that point on, the control thread will create the tasks. Firstly, the initial task full is created with the directive task. Then, the two bar tasks that depend on the full tasks. And finally, the four fun tasks that depend on the bar tasks are created. All this execution is controlled by the OpenMP runtime. The control thread first submits its tasks to the runtime. The runtime in turn stores these tasks in a dependence graph. Whenever a task has all its dependencies satisfied, it goes to a ready queue. Once in this ready queue, the tasks are available to be executed by one of the worker threads. These worker threads operate using the work stealing tactic. This whole process is executed automatically by the OpenMP runtime, without interference of the programmer. Besides creating tasks, the OpenMP specification has the target directive that allows offload data and computation to an accelerator device. In our project, we set the FPGA as an OpenMP accelerator. As you can see in this piece of code, we use the target directive along with the device clause to specify the computation offloads to an FPGA. The map-to clause specifies the data we want to send to the FPGA, while the map from clause specifies the data we want to bring back from the FPGA. The OpenMP specification also allows us to combine the target and depend directives to create a graph of tasks that will be executed on a device, and it is exactly this feature that we will use in our project. However, the LLVM OpenMP implementation has some limitations for multi-FPGA architectures. 1. It does not support bitstream offload to multi-FPGAs. 2. It does not support mapping data dependencies to IP and board interconnected. And 3. It does not allow a seamless flow of data to and from multiple FPGAs. And it is exactly these limitations that our proposal seeks to address. To achieve this, we need first to work on the LLVM compilation toolchain, more precisely the libump target library. The libump target library provides an agnostic offload mechanism in which to add a new device to the list of devices that the OpenMP runtime supports. One just needs to create and add a new plugin to the library. This figure shows how the libump target library interacts with the system. First, the clang generates a fat binary with the host and target's appropriate representations. At the moment that the program reads the target directive, the library checks if the plugin is compatible with the target binary, then maps the data environment and executes the computation on the device that was specified. What we did was add a plugin to the board we are using, the VC709. This plugin will manage the entire communication mechanism with the board, as well as map the dependencies between the IP available in the FPGA cluster. On the hardware side, we also need to add support to execute on a single node and on multiple nodes. First, let's talk about it. Execute on a single node. As previously said, we are using the Xilinx VC709 board, which is equipped with two 4GB memory chips, 8-lane PCIe module, and 4 SFP Plus interface. Each SFP Plus interface allows a communication of up to 10 gigabits per second, reaching a total of 40 gigabits per second of bandwidth in the optical fiber. Besides the physical components of the board, the kit also comes with a target reference design, featuring a PCI Express IP, a DMA IP, a network module, and a virtual fifth memory controller. This is the base platform on which we'll build our hardware. The first modification we made was the insertion of the module AXI4 string interconnect. This module allows the tasks that are within the FPGA to communicate with each other and is configured by the bank of registers. These IPs are hardware modules that perform the tasks. The hardware design will only have to create IPs that implement the XI stream interface and plug them into these black boxes. For example, imagine that you want to create 4 tasks, each incrementing +1, +2, +3, and +4 successively. First, you need to create a pool of work threads with the OpenMP parallel directive. Then, select the control thread with the OpenMP single directive. This for loop uses the target directive along with the device clause to create the 4 tasks. The map clause specifies the data we want to send and bring back from the FPGA. In this case, is only the vector A. The depend clause will guarantee the order of execution of each task, and the no wait clause allows the tasks to be executed in a non-block way. With this graph of dependencies, The plugin maps the executions to the available IPs. Firstly, executing the IP plus 1, then the IP plus 2, then the IP plus 3, and finally the IP plus 4, finishing the execution. We also propose solutions to execute on multiple nodes of FPGAs. At this moment, we have a cluster with 8 FPGAs connected through optical switch or point-to-point. For multi-node task execution, we needed to forward dependence data across optical links. And for this data to be able to pass through the fiber, they needed to be in a MAC frame format. For this reason, we designed a module called MAC Frame Handler that is responsible for mounting and unmounting the MAC frame. That way, the IP will work only with useful data. The MAC frame has the following format: 6 bytes of source address, 6 bytes of destination address, 2 bytes for the size, and the rest is just payload. The MAC frame handler is located between the virtual FIFO and the XI string interconnect modules. Intercept all data that arrives, remove the headers, or leaves the FPGA, adding the headers. It is also configured through the configuration registers. For example, imagine the same program as before, now executed on 2 boards. First, the data would come to IP plus 1. It would pass through the interconnect module and then arrives at the MAC frame handler. This module adds all the information in the frame header, so that the data is able to pass through the fiber. Once on board B, the procedure is the opposite. The MAC frame handler module removes the header information and delivers only useful data to IP plus 2. This IP sends its data to IP plus 3, and from that point on, the data goes the other way until it reaches the IP plus 4, and finally ends the execution. Right now, we have ongoing experiments with stencil application that computes the Laplace equation in 2 FPGAs. The execution flows similar step as before, going through all the IPs on the board A, then going to the board B, going through all the IPs on that board, and finally return the result to the board A. Stencil applications are widely used in a wide variety of scientific applications, including seismic imaging that motivated our project. Throughout the literature, it is possible to find some works that somehow try to integrate FPGAs with OpenMP. However, none of them present solutions for the execution in multiple FPGAs. This table summarizes the main works published since 2006 until now. We are giving special attention for this work from 2018, called Hard Cloud, which was published by our research group. The target architecture of this project was the Intel HARP2 and the FPGAs in the Amazon clouds. Hard Cloud was our first step in integrating FPGAs into the OpenMP program model. With this new project, we seek to expand our solutions for multi-FPGAs architectures and incorporate the task model, thus differentiating our work from other proposals. The main differences from our proposals to the existing ones is the fact that we use OpenMP tasks in multiple FPGAs architectures. That is all for this video. I hope you have enjoyed. Thank you.